Okay, so we continue with the second talk of this session. Now with us is Daniel Nussko, and he will tell us about how much fun he has with IoT firmware. Enjoy.
Hello and welcome to my talk. I will talk about the security of IoT firmware. I conducted a large-scale security analysis on IoT firmware, and in this talk I want to give you a high-level overview about what I've done and my results. A few words about me. My name is Daniel Nussko. I'm from Germany and working as a penetration tester. So my job is to discover vulnerabilities in corporate networks and applications. I have a special interest in the field of IoT security. That's why I conducted a static analysis on firmware, and that's my topic for today. Before we start, a short introduction. Why are IoT devices interesting, and especially, why should we care about the security of them? Well, today we have more and more connected devices in our homes as well as in corporate networks. For example, we have home automation systems, which we can manage by our smartphone. We have smart speakers that are connected to a Wi-Fi, and of course a lot of regular internet devices like a router, a surveillance camera, a VoIP phone, and so on and so on. But we also have more and more industrial devices, like industrial control systems to control machines. We have robotics or solar power systems. All of these devices are connected to our networks because we want to monitor and manage them. So you see, IoT devices are more and more common and more widespread. Today we have about 36 billion devices worldwide, and the number of devices rises from year to year. So in 2025, we expect to have more than 75 billion IoT devices. And all of these devices are connected to our networks, and some of them to the internet. So what does this mean? Let's take a look in the past. In 2016, we had about 18 billion devices, and in the same year, the Mirai botnet compromised about 600,000 IoT devices. And these devices were responsible for very large distributed denial of service attacks. For example, one of these attacks hit one of the internet service providers of Liberia. And this attack was so heavy that the internet connectivity of the whole country was temporarily interrupted. So according to the statistics, we will have 4 times as much devices in 2025 as in 2016. Additionally, you have to know that the original version of the Mirai botnet just used a simple list of default credentials. So compromised devices scanned the internet for SSH or telnet services and then tried to log in with default passwords. And I assume that much more devices can be compromised by using publicly available exploits. So we have more and more devices. All of these devices are connected to our network. All of them have interfaces to manage them. For example, a web interface. Some also provide other network services, which all pose an attack surface. So the security of IoT devices is known to be poor, but what are the reasons for such a bad product security? Well, as devices are often produced as cheap as possible, there is a hard competition between the vendors. Product security costs money, and I think it's not the vendor's first priority. In addition, these devices are very diverse and very individual, not only the hardware, but also the software. A lot of software components are developed by the vendor itself, which increases the risk of design flaws compared to well-known and standardized components. And IoT devices have a short life cycle. I will come to that point later at the end of my talk. Okay, before we start diving into a large-scale analysis, I want to share my experience from a penetration test. I conducted a penetration test of a security camera, and now I want to mention 3 of the identified vulnerabilities. A buffer overflow, which was located in the web interface of the device, and a denial of service vulnerability, also affecting the web interface. And also here, in this case, the web server binary was self-developed by the vendor. I've seen this many times before, that vulnerabilities are often located in self-developed components. And I've identified a debug interface that can be accessed over the network. This debug interface allows, for example, to create memory dumps. The interesting thing about that IP camera was that this device was white labeled. So on the camera there was the company logo of a German vendor, but in fact the device was produced by a Chinese manufacturer. And a little research showed that this manufacturer is the 2nd largest manufacturer of IP cameras in the world. And a little more research showed that IoT devices from this manufacturer were significantly involved in the Mirai botnet. So it seems that the circumstance that this device was white labeled and at the end sold by another vendor led to several problems. First, when I informed the vendor about the debugging interface, which was enabled by default, it turned out that the vendor didn't even know about that feature. And second, it turned out that some of the identified vulnerabilities are already known by the Chinese manufacturer and are also fixed in a newer firmware version. So someone took a closer look on this device, discovered vulnerabilities, reported them to the manufacturer, and the manufacturer released a new firmware version where they have been fixed. So this is the best case you can get. And even here, these devices stay vulnerable because of communication problems between the original manufacturer and the German vendor. So the German vendor didn't know about the new firmware and shipped these products with the old and vulnerable firmware version. So this example shows that there can be many different reasons that lead to bad product security, not only programming mistakes. Okay, since we cannot rely on product security, we need to evaluate the security of these devices. Therefore, several approaches exist. We can perform a penetration test. Here we'll look at the device and its interfaces while it's in operation. For that, of course, we need the physical device. But the advantage is that we can analyze this device in depth. So we get very accurate results because we avoid false positives by verifying the vulnerability directly on the device. But this approach simply does not scale. So this is not practical for a large-scale analysis. We also have the possibility to emulate a firmware. We can use QEMUR for the purpose, but this is hard to apply because the hardware of IT devices is very diverse. Usually, if you try to dynamically execute a firmware, it is checked if the peripherals are connected and working. The device may have a sensor or a camera or a physical button, which we don't have when you emulate them. There also have been attempts to emulate only single parts of the firmware, for example, emulating only the web interface. This approach allows to run common vulnerability scanners on the web interface, although the device is not physically present. But the setup for this is really complex, and it's very difficult to automate this process for a large-scale analysis. This is the reason why I chose a static analysis. In this approach, we unpack the file system and the binaries and all the files in the image, and then we analyze them. And of course, this approach is much more limited because we don't have the device up and running. It's scalable, and we can automate this process to analyze a large amount of firmware files. The aim of this research was to obtain a high-level overview about the security of IoT devices. Therefore, a large number of firmware files from different vendors and also different device types were collected. And due to the large number of firmware files, it was necessary to fully automate this process of firmware unpacking and analysis. So at the end, every firmware file was analyzed with regard to several topics. First of all, name and version information of common binaries and system libraries have been identified. So in the first step, the file type was identified, and in case of an executable file, like an ELF file, printable strings were extracted. And after that, these strings were analyzed using regular expressions for typical version information. So the name of typical software components like OpenSSL, BusyBox, or OpenSSH, along with their numerical software version, was extracted. And yeah, in this way, it was found out which software has been used and in which version. For that, I use regular expressions in combination with YARA files. YARA is a signature format which was originally developed for malware detection and is used for antivirus software. Then I checked every binary file for the use of compiler-based exploit mitigations. To give an example, when compiling a program with GCC, you can set different compiler flags to make exploitation of buffer overflows much more difficult. Another aspect was the analysis of default user accounts. In this case, the passwd file and the shadow files were analyzed, and the password hashes have been extracted from the shadow files. And after that, a dictionary attack was conducted to recover as much plaintext passwords as possible. And in the last step, cryptographic material was identified, such as certificates, private and public keys. This was also implemented by signatures in YARA format. So how do we perform a large-scale analysis? There are several tasks to do. First of all, we need to collect the firmware images. After that, we need to unpack the firmware file in order to access the directory and file structure. And when this is done, we are ready to start to analyze the processes. So for every file, a set of checks is performed. We check the file type, and in case of an executable file, we analyze if exploit mitigations are implemented. We scan the file for version strings and also cryptographic keys and certificates. All results of this analysis are stored in a database. In addition to the results, I also collected some metadata of all files, which I also store in the database. For example, I created a hash value of each extracted file, and this allows me to analyze if a specific file is also present in another firmware image. So in case we have a finding, let's say a hard-coded certificate, we can use the hash value of this file and search in our database if this specific certificate is also present in another firmware image. When our automated analysis is finished, we can use our database to create statistics about the results, or to search for files in a specific image and to manually analyze them afterwards. All right, let's take a look on the architecture of my analysis environment. During my first tests, it got clear that the analysis has high system requirements. A large number of files is examined in parallel, and therefore the analysis scales with the number of available CPU cores and the system memory. And this was the reason why I decided to run the analysis in a cloud environment. The analysis itself was implemented in Python using the FACT framework. As the FACT framework is built modular, it's easy to create custom modules in Python. So as you can see here, we have different components. We have the firmware analyzer server. Here we unpack the firmware of images and analyze the files. All unpacked files are stored on a virtual cloud storage. we keep all unpacked files since we may want to analyze them manually afterwards. And we have a database server. This database server is based on MongoDB, and here we store our results. All these components here are located in the cloud. I've also developed a job scheduler that uploads a firmware file to the analyzer server and monitors all tasks on the server. This is done by a REST interface. Where did I get the firmware from? I downloaded the firmware files from the manufacturer's websites or FTP servers. I only collected firmware images that are directly provided by the manufacturer itself. And doing so, I can be sure that I analyze the original firmware from the vendor and not any other image that might be customized by someone else. To automate the process of downloading of firmware files, I developed a crawler in Python based on the Scrappy framework. And in this way, I crawled download pages of 20 vendors and downloaded about 10,000 firmware files. So I manually searched for the download portal of a vendor, and then I crawled the portal for firmware files with my Python script. Together with the firmware itself, I also stored some metadata about the images. For example, I generated a hash value of each firmware file just to avoid duplicates, or I stored the URL where I downloaded the firmware file from. As you can see on this pie chart here, most of the firmware images are for routers, followed by security cameras, printers, switches, and VoIP phones. And a smaller number of images are for NAS systems, smart speakers, Wi-Fi repeaters, VoIP gateways, photovoltaic systems, smart locks, smart plugs, and power line adapters. So as you can see, a wide range of device types were analyzed. So let's talk about the unpacking of the firmware file. Most of the devices I analyzed have a full operating system. So you have a kernel, you have a user space, and a file system. And the firmware files are often packed in multiple layers and different file formats. So the challenge is to handle a wide range of file and archive formats and to unpack them in an automated way, layer by layer. Manufacturers often provide firmware files in an archive file, and after this archive file is unpacked, you often get a binary blob. And to extract files from this binary blob, we use so-called file carving. This means we search for common file signatures and magic bytes within this binary blob and then try to extract this file. And one very good tool for this is Spinwalk, which I also used here in this case. This is a very well-known tool and very popular for firmware reverse engineering. Okay, let's take a look on the results and start with some general observations. The results here show that the majority of the analyzed firmware files were based on the Linux kernel. So in 88% of all firmware files, a Linux kernel was identified, with about 6% thread access used, which is a proprietary operating system and often used for consumer electronics. In 2% of the firmware files, OpenWRT is used. This is a Linux-based operating system used for routers. Then we have a very small number of devices which use VxWorks, WindRiver Linux, and Lynx OS. On the right side, we see statistics about the identified CPU architecture. Most of the devices are based on MIPS and ARM CPUs. This is very common for IoT devices, but we've also some architectures that are not that common, like M68K from Motorola or Super H, a microcontroller from Hitachi. This chart here illustrates the number of times a specific software component was identified among all firmware images. The most commonly identified software is OpenSSL, followed by BusyBox, which is very common for embedded Linux. This is a single executable file which combines a set of command line tools. We also see some binaries that provide common network services, like UDHCP, OpenSSH, DNSMask, and Dropbearer SSH. And for all these programs, also their version has been identified, and in this way, we got an overview about the use of outdated software components. Okay, here you can see the version landscape of OpenSSL as an example. So we see how often a specific software version has been used. And actually, this is not the complete list, as the complete list would be much too long. These are only the most frequently used versions. The extracted version information was then compared with data from the National Vulnerability Database, from the NIST Institute, and in this way, for each version, already known vulnerabilities and also their CVE numbers have been identified. As example, the bar graph on the left shows the number of vulnerabilities according to their CVSS score. In this case, for OpenSSL 0.9.8z. In this way, we can find out vulnerabilities which affect this version and also their severity. Just some interesting statistics regarding 3 famous vulnerabilities in OpenSSL. According to their version information, about 75% are affected by the freak vulnerability, about 50% by Poodle, and about 6% by Heartbleed. Here, OpenSSL is just an example. I created such kind of statistics for all software components, also for the identified Linux kernel. So the results for the Linux kernel show that 2 of 3 kernels are older than 10 years, and more than 90% of all Linux kernels already reached the end of life. And the oldest Linux kernel I found was from 1997. When I crawled the download portals, of course, also firmware images from old devices was downloaded, so it was not possible to distinguish between old and new devices. This is something you have to do manually, so you have to look for the release date of a firmware, maybe on the website of the manufacturer, or take a look in the changelog. You cannot do that by an automated analysis. That's why I did some manual research and compared the release date of some devices with the kernel version. The results differed very strongly from manufacturer to manufacturer. It turned out that at product launch of some enterprise VoIP telephones, for example, a kernel version was used that was already 10 years old. So even current high-end phones, which are dedicated to the enterprise market, are sold with a strongly outdated Linux kernel. Let's take a look on binary hardening statistics. All ELF executables and libraries are checked for the use of common exploit mitigations. So when you compile a binary, you can set different compiler flags to make use of them and to make exploitation of buffer overflows much more difficult. And here you can see the results. When compiling a program with GCC, NX, the no execution bit, is set by default. I think this explains why 90% of all the analyzed binaries make use of NX. As far as I know, all other protection mechanisms like stack canaries, relrow, and fortify source must be explicitly enabled during compilation. And I think this is the reason why they are not that present in most of the binaries. Okay, as already mentioned, I also analyzed the passwd and shadow files. This chart here shows the number of users which are allowed to log into the operating system and for which a hard-coded password is set in the shadow file. So all of these users here can be used to log into the device. Several of them show typical usernames for factory default accounts such as root or admin or guest or user. But you can also see some users which have cryptic names. And in the past, we've seen several cases where such cryptic names have been identified as undocumented static user accounts. So in case an SSH or an Telnet service is running, these accounts can be used for remote access to the device. And some of these cryptic usernames here in this list are already known, and you can find CVE numbers about them, but others are still unknown. So yeah, static user accounts, especially when they are undocumented, are a real problem. From all shadow files, I extracted the password hashes and performed a dictionary attack on them to recover weak passwords. And the results show that pass was the most common hard-coded password, followed by 1234 and an empty password. And all in all, 68% of all hard-coded passwords have been recovered by the dictionary attack. Another interesting fact, the Mirai botnet used a total of 62 combinations of usernames and passwords, and 12 of them were also identified here in this research here. Please keep in mind that these are the results of a static analysis. We don't even know if there's a service running that allows user login. In addition, we cannot know what happens on runtime. So this is like a snapshot of the device software which we shot before the first boot of the device. And maybe after the first boot or during the first boot process, the user is forced to change default credentials. So this is one of the disadvantages we have when we conduct a static analysis. As part of the analysis, also cryptographic keys and certificates have been extracted. This table here lists the number of cryptographic keys by their type. Most of them are TLS certificates. Among them are a lot of root certificates, but also hard-coded and self-signed certificates. Also, a lot of RSA keys have been identified. Some of them belong to their corresponding TLS certificate. Others are used for SSH. Regarding SSH, most of the RSA keys are identified as SSA host keys. A few public keys are used for key-based authentication. I will come to that point later. So what's the problem with hard-coded keys? Let's have a look at the principle of asymmetric encryption. On our device, we generate an individual key pair, let's say RSA keys. So now we have two different keys, a public key, which we provide to our clients, and the private key, which we keep secret on our device. Our clients are now able to encrypt a message using this public key, but the only one who's able to decrypt this message is the owner of the private key. So the security is based on keeping the private key secret. In case of a hard-coded certificate, all devices with the same firmware use the same public and the same private key. So, for example, the device may use these keys for HTTPS communication to the web interface. In this case, an attacker could easily decrypt the TLS traffic just by extracting the private key from the firmware. The firmware is publicly available on the internet, so extracting the private key should not be a problem. In many firmware files, I've seen hard-coded certificates and hard-coded SSH host keys, but also here, we cannot absolutely rely on the results because the device may regenerate a pair of keys during the first boot process and then overwrite this hard-coded key pair with an individual key pair. And we simply cannot verify that with a static analysis. Now we've seen that hard-coded cryptographic keys are not a good idea, but there is also another problem. Hard-coded TLS keys can be used to identify IP addresses of publicly reachable devices. And here you can see an example where I use Shodan to search for IoT devices by a specific certificate fingerprint. As the certificate is hard-coded, all devices use the same certificate with the same fingerprint. That means that I can use this approach to identify the IP addresses of all internet-reachable devices. And this can be used to conduct very, very targeted attacks on specific device models. For example, to connect to these devices with a hard-coded password that I've extracted from the firmware before, or any other attack. After the automated analysis finished, I had a large database of extracted files and a lot of metadata about them. I used this database for further manual analysis. For example, I used metadata of all identified RSA keys to search for the file name authorized keys. This file allows key-based authentication, so the owner of the private key is able to log into the device in case an SSH service is running on a device. In firmware images of 4 different routers, I found an authorized key file. 3 of them offer an SSH service according to the user manual. So I contacted the affected vendors and described the problem. One of the vendors rejected the problem and claimed that key-based authentication would be disabled. A little research showed that for Dropbearer, which was used in this case for SSH, you cannot do that by configuration. So you have to compile the executable without key-based authentication. So I did that and compared the binary I've extracted from the firmware with the own compiled one. And then I searched for the function call used for key-based authentication, and I also found it in the extracted Dropbearer executable. So I'm pretty sure that key-based authentication would be possible and that the owner of the private key is able to log into this device. But I cannot prove that without having access to one of these devices. Okay, I also analyzed all extracted files with regard to suspicious strings. Thereby, I found a CGI script, which is part of the web interface. I've identified this file in firmware files of 9 different device models. When the CGI script is called, a telnet service is started, and a new user is created. And this script was identified in different versions. In a newer version, an SSH service is started instead of telnet. The name of this new created user is NSA Rescue Angel. All of the affected products are network-attached storage systems, and most of them are from the vendor's product line called NSA, so I think that led to the username NSA Rescue Angel. I reported that to the vendor. The vendor confirmed the backdoor and stated that this was used for troubleshooting during development. For 4 of the affected devices, a new firmware version was released. But the other 5 products will not receive a security patch as the support period already ended for them. And this is due to the short product lifecycle of IoT devices, so these devices will stay vulnerable forever. Okay, I also want to mention that I've identified some, let's say, unusual software components in device firmware. For example, TCP dump. TCP dump is a tool which allows to capture network traffic. I found TCP dump in 500 firmware images of 8 different vendors, mainly in firmware of routers and VoIP phones. So in case of a router, I could imagine that capturing network traffic might be a helpful feature for troubleshooting, for example, but I have no idea why you should need it for a VoIP phone. In addition, I've identified GDB. GDB is a debugger used for runtime analysis of executable files. I was surprised how often I found GDB in firmware files, all in all 861 times from 9 different manufacturers. GDB was mainly found in firmware of security cameras, routers, and switches. And it seems that developers forgot to remove these binaries, but it's definitely not a good practice to leave that components in the image and to ship the products with them to the customer. Now we come to the end of this presentation. To sum up, we've seen that it's possible to automate the process of firmware analysis. In this research here, a total of 10,000 firmware files were automatically unpacked and analyzed. And the results show that, there are a lot of best practice violations. Vendors use hard-coded credentials, hard-coded keys, they forget to remove SSH keys, and they even ship their devices with a backdoor. A lot of software components are outdated. We've seen that more than 90% of the used kernel versions are out of support and are affected by publicly known vulnerabilities. And we've seen that vendors do not make a good job in binary hardening. A lot of compiler-based exploit mitigations are simply not used. Thank you for your listening. I think we now have some time left to answer your questions. Thank you very much.
So, thank you. So, the first question is here.
Thanks. Concerning debugger and TCP dump, I've seen firmware images where TCP dump was used to provide a debug dump when something goes wrong. So I think there are legitimate uses for TCP dump. For GDB, I'm not so sure. Concerning the versions, when you download automatically, you might find from a single device lots of different firmware versions, and only the latest one is supposed to be installed on those devices. What did you do about that version problem?
Yes, that's a really problem. When I crawled the download portals, all of the firmware versions has been downloaded, and I also analyzed all of these files. But I stored in the database which version has been analyzed with this firmware version. So in most cases, according to the file name from the download page, you can identify which version is used. So but you are right, this is something you have to do manually. You have to compare the model and the firmware version, and then take a look which firmware version is the newest one. So before you report something to the vendor, you have to do this manually and check if the vulnerability is located in the latest version you have analyzed.
Yeah, thanks for your talk. I have a question regarding the firmware extraction. Usually vendors are bad in security, but they're getting better, and now they start also with encrypting and signing the firmware images. So I wonder how many images were unable to get extracted, maybe because of encryption or just a crazy compression algorithm.
That's true, yes. In case of an encrypted firmware image, it's not possible for me to analyze this in an automated way. So these firmware images were just skipped. I thought about to identify if a firmware image has been encrypted, but this is very difficult. You can take a look on the entropy of the file, so you can analyze the entropy of this firmware image, but in case of a high entropy, it might be encrypted, but it could also be the case that it's just an archive format which you don't understand. So an encrypted image has a high entropy as well as a zipped or a compressed firmware images. So yeah, it's difficult to identify if it's encrypted or just packed.
Have you tried to identify how much % of the devices have actually an outdated firmware running with Shodan?
No, I just did some manual analysis with Shodan, but I did not automate this process for all firmware images.
Concerning the encrypted firmware, did you do a statistics how many firmware images you were not able to unpack for one reason or other?
No, I don't have any statistics. I just skipped these firmware files and didn't analyze them. Yeah.
So, are there more questions? No, then one question from myself. Did you only use like open download portals or also websites where you need an account? or only by like free registration, or did you also contact vendors to give you an account for firmware that's behind a paywall?
I only collected firmware files that are directly provided on the website, which are publicly available. Not any firmware files which are downloadable after registration. So just these which are publicly available.
Do you plan to continue and maybe ask vendors to open their paywall for you to analyze the images, or you think nobody will give you access?
I'm not sure. I think there's also a legal problem in case when you take a look on the general terms and conditions on the download portal of different vendors, there's stated that reverse engineering of the firmware file is prohibited. So you're not allowed to reverse engineer that, and I'm not sure how the vendors react when you offer them to analyze these firmware files.
Just a follow-up question. How many GPL violations did you find? Because during the analysis, you know what GPL software is used, and actually you could also automatically download the source code or actually ask for the source code, and then you can find the evildoers.
I didn't analyze if any GPL violations have been happened. I think this is also something you have to do manually when you take a closer look on the unpacked files, which software components have been used, under which license this software is released, or if the source code is available on the website or not. I think this is difficult to automate this process. But yeah, you can do it manually afterwards. Okay, in case there are any other questions, I think there's now the coffee break. Just ask me on the floor.
There's one more question from the stream, or a comment. As far as I know, it is quite common in VoIP devices to have the network dump option in web interfaces, so you could consider it, couldn't consider it as unusual.
Okay, so this is new for me, yeah. Okay, that could be a feature in VoIP phones. I've seen this for routers, for traffic dumps, but not in any VoIP phone. So that might be a plausible explanation.
Okay, I think there are no more questions. Then thank you, Daniel.
Thank you too.